Today I will talk about the electrolytes design for high energy lithium-ion battery. First, I talk about the lithium-ion battery actually consists of anode and cathode. Anode is graphite, cathode normally transition metal oxide. And during the discharge, the lithium subtle between anode and cathode. And right now, lithium-ion battery has been widely used in the transportation, consumer electronics, grid energy storage. The reason is just recently, the lithium-ion battery, the cost is significantly reduced. And this green line is the graphite transition metal lithium-ion battery. So this is the cost, this is a year. And right now we are in the 185, and they expect at a few years later that we can reach to the 100 or below. If we use the silicon replace the graphite, and we follow this line, and the cost will reduce more significantly than current graphite anode battery. And then if we use a lithium metal, and then the cost even lower, and because they have a high energy. So the DOE considers three kind of chemistry: current graphite, and near future silicon, eventually lithium metal. For the graphite, they expect highest energy density is 300, and they have a challenge is fast charge, low temperature performance. And because if you have a fast charge, they will form a lithium dendrite, and they will catch fire. Low temperature, same challenge. So this brings the same issue as if we use lithium metal. So if we solve a lithium metal problem, and then this will not a problem. And second is silicon. If we use silicon replace the graphite, the energy density can be increased from 300 to 400. But they have a problem is calendar life, also the cycle life. And eventually they think they should go to the lithium metal. And lithium metal, they have a problem is lithium dendrite. And so the cycle life and safety is concerned. So today, I will talk about electrolytes design for three types of battery chemistry and why they are different, and how can we design future electrolytes for high energy lithium metal battery. So this is the lithium potential, referred to lithium. And this is the aqueous. Aqueous electrolytes, they use water. So the stability window is limited by intrinsic of stability of the water. Even you consider the hydrogen evolution over potential, and normally the window is less than 2 volts. That is significantly limited energy density of aqueous. And then they go to the organic. Organic different is water reduce, they form gas, but organic, they can potentially form solid polymer. When they form polymer, they can passivate. Then they have a chance they can form solid electrolytes interface. And interface protect the anode, allow graphite to cycle at a very high Coulombic efficiency. So this 99.98 allow graphite to cycle 1,000 times. So the success of graphite anode is because this electrolytes can form organic, inorganic SEI. The reason is when lithium move to the anode side, the solvent reduce and form a polymer, and ion reduce form a ceramic. So this is form composite because their reduction potential similar. Also a lot of solvent along with the lithium. But they have a challenge is low temperature or fast charge, because as I mentioned, when you have a fast charge, they potentially form lithium dendrite. But if we have a method that can solve the lithium dendrite problem, and then this will automatically overcome this challenge. So we propose use lithium fluoride rich SEI. They can suppress the lithium dendrite. This method can be applied for graphite, the battery, for fast charge, also low temperature operation. So to further increase the energy density, the DOE, the goal is use AMC, replace the lithium cobalt oxide, also use the silicon to replace the graphite. So silicon or lithium, both they have a very high capacity than graphite, but unfortunately, if we use the same electrolytes, we got a Coulombic efficiency only 90, so very small compared to graphite. Why this happened? This is because silicon volume change is big. Khalil just showed this figure. When you have a high capacity, meaning is larger amount of lithium come into the alloy with silicon, volume change 300%, graphite only 12%. Then they will crack. When they crack, if you form SCA, same as graphite, organic, inorganic, they strongly bonded with the silicon. When silicon volume change crack, SCA also crack because SCA, organic, inorganic, the plastic deformation capability cannot accommodate 300% of silicon volume change. And also, if you have a lithium, the volume change even bigger than silicon, and then they will crack and lithium will come out SCA, and then they form a dendrite. If we use MC811, the capacity 200 and lithium cobalt oxide only 150. They already report AMC when you cycled, they also form a crack because the volume change larger. So they have the same problem. Traditional, the way to solve the problem is they want to form really polymer coated on the surface, the very flexible plastic deformation. But if you talk about a 1,000 cycle, repeat volume change, is no any material can accommodate such a large volume change. So we think different. We want from ICA, they can have a less bond with the substrate, like silicon, lithium, MC811. Then when silicon volume change, SCA not bonded. So meaning SCA will stable, not broken. Only silicon inside shrink and expanded. So that make the electrolytes outside cannot penetrate. If they cannot penetrate into the crack, then they have a chance self-healed. Because lithium silicon, when the lithiation content is high, they are plastic. So meaning they can flow and they can heal the crack. So the lithium is the same thing. We want from lithium fluoride SCA because they have a high interface energy, meaning they bond very weak. So they have two advantages for weak bonding. One is when lithium ion come here, cross, becomes the lithium atom of the charge transfer. And then they can easily diffuse, migrate along the interface because they bond very weak. Even you have a chance crack lithium penetrate inside the lithium fluoride SCA because the interface energy is such very high. Any area increase, they will add additional energy penalty. So similar, if you consider lithium as a liquid and as a water, and then this is a PTFE, even you have a crack, water cannot penetrate because HFE is hydrophobic. So the same principle, when we want to block a lithium dendrite, we have to use lithium phobic SCA, not a lithium philic. Polymer normally is lithium philic, and so they are lithium dendrite easily penetrate. And if we use lithium fluoride, and they have a very high interface energy and highly lithium phobic, and lithium cannot penetrate inside. Same principle. If AMC crack, if you have a lithium fluoride, and then they can protect, AMC can crack inside the sealed lithium fluoride, and then electrolytes will not come inside. And then we think why we select lithium fluoride, and then we calculate all the potential inorganic compound can be formed in the SCA. And we find out lithium fluoride has highest interface energy with the lithium metal. And also because lithium fluoride bond themselves very strong, so they do not have a chance to bond to others. So that's the reason they have a high interfacial energy with MC silicon also. Second, mechanical strong. If you can multiply these two numbers as indicator for lithium dendrite suppression capability, this number much higher than others. So this is a negative one. This is LPS, solid electrolytes, meaning LPS cannot prevent lithium dendrite. Second reason we use lithium fluoride is they have a very lower electronic conductivity. This is a band gap, and lithium fluoride has a widest and the band gap. The meaning is electronic conductivity is lowest. If electronic conductivity is lowest, meaning is when lithium fluoride grow very, very thin, they will stop the tunnel effect. So they will have formed very, very thin SEI. Very thin SEI meaning is consume lithium less. Irreversible capacity is low. That is normally we want. And third one is the stability window. Lithium fluoride has a wide stability window compared to others. That means lithium fluoride will stable even at 6 volt. They can use as cathode CI. So combine of this, the property, we believe lithium fluoride is the best, both for anode and cathode. Second, how can we form lithium fluoride SEA? So we know lithium fluoride mainly come from ion. Solvent, normally, even you use fluorinated solvent, they also form polymer. So we want to increase the concentration of PF6 or FSI and suppress the solvent reduction. That means we need to add more PF6 and reduce solvation of the lithium to the solvent. So we have to select the solvent has less solvation energy. So in this case, we want to reduce the solvent in the solvation and increase the bond between the lithium and ion. So the idea principle is if we really want to form high concentration lithium fluoride, we have to increase the concentration of ion. Second, we have to enlarge the reduction potential difference. Even old ion and the solvent move to the anode side. And if ion has high reduction potential, they will reduce first from lithium fluoride. When lithium fluoride on the surface, they can protect the anode and suppress solvent reduction. So this both are important. So the design is we use two strategies and to increase the concentration of lithium fluoride in the SEI. First, the simple idea is increase the concentration of ion. Then easy way is increase the salt concentration. When we increase salt concentration, we can increase the AGG and the CIP. So in that case, one lithium, they can bring more ion with the lithium to reach to the anode. So one idea is 10 molar lithium FSI in the ECDMC carbonate. So we really can increase the Coulombic efficiency from 90 to 99.2. But this is compared to graphite, still too small. And then we think, is there any way we can further increase? Also, when you have a high concentration for salt, the cost increase, also viscosity is high. We think we should reduce the salt concentration, and then we add, we call it anti-solvent, HFE. HFE, they have special properties. They can dissolve the solvent, but they cannot dissolve the salt. So in that case, they can reduce the solvation energy. Also, they can reduce the salt concentration because they are not dissolved salt into the HFE. So we get the similar the Coulombic efficiency, but with much lower salt concentration, also viscosity much lower. And additional advantage, we also add fluorine on the carbonated solvent, FEC, FEMC. And here the reason is even solvent reduced, they still have a chance to form lithium fluoride. And second advantage is fluorine on the right side of oxygen. When you talk about catch a fire is oxidation reaction. Fluorine on the right side, they cannot be burned. So if we add fluorine on the solvent, they will not catch fire. This is the first strategy. Second strategy is increase the potential reduction potential difference. And for example, we use THF. THF has very lower reduction potential, but ion, they have a very high reduction potential, PF6. So they have a huge gap. This is 1 volt, this is 0.3 volt. We hope when we reduce the potential, ion first reduce, and then after they form lithium fluoride, and then they have a chance for polymer. But the polymer, because the anode already protected by lithium fluoride, THF, even when potential reduced to 0.3 volt, they cannot reduce, only at a very lower potential or lithium fluoride crack. So we use this electrolytes, we only put 2 molar, and we also put the lithium philic, the substrate, make sure lithium plating is uniform, because we use a lithium philic graphite bismuth mixture as the substrate. And on the top of lithium, we use lithium fluoride rich SEI. This is lithium forbic. So forbic, lithium forbic on the top, lithium philic on the bottom. In this way, we really got 99.8 Coulombic efficiency. This is as we talk here, this is universal, not only for lithium. It should be work silicon, also AMC. Then we check the silicon, same electrolytes, and then we put the micro-size silicon, because if this concept is right, the crack doesn't matter. So we can use micro-size. We tried the micro-size 30 micron, and we can get a Coulombic efficiency 99.9. Because silicon, everybody believe it should be nano, and micro-size never successful. Based on this concept, we make the micro-size silicon 30, 40 micron can cycle very well. So the design principle is suppress solvent reduction. And is there any way we can not use the solvent? That is ionic liquid. But the ionic liquid that bring additional problems, cation may be reduced. So we synthesize special ionic liquid, and we can achieve 99.9. The principle is they form almost pure lithium fluoride and also inorganic SEA. And they are strongly lithium forbic, they can suppress lithium thunder. Another case, special case, no solvent is solid state. Solid state, no solvent. Support should be similar as organic liquid. But unfortunately, we cannot form lithium fluoride. And because it's hard to dope fluorine in the LZO. And the Coulombic efficiency much lower. The second reason is the LZO, they have a certain electronic conductivity, 10⁻⁸. Liquid is infinity, meaning no any electronic conductivity. Electronic conductivity can potentially deposit the lithium inside the electrolytes along the green boundary. So that brings the Coulombic efficiency lower than traditional liquid electrolytes. And for the LPS sulfide electrolytes, they can potentially bring chloride. We know the lithium chloride also have a very high interfacial energy with the lithium, but not as good as the lithium fluoride, but at least better than LZO. So the LPCl, and they can reach high Coulombic efficiency. So the challenge for solid state is if you form artificial lithium fluoride, it's not very useful because they cannot self-heating. Lithium penetrate, and then they can directly react with the inside the bulk solid state electrolytes. So we have to modify the solid state electrolyte themselves from lithium forward, the ICI when lithium reach to the solid electrolytes. Then we want thinking, is there any idea lessons the success on the liquid electrolytes can be used for solid state. And we know we can use the anti-solvent. Anti-solvent is they are not an ionic conductor because they are not dissolved salt, but they can help localize the high concentration. And for the beta alumina in the sodium ion battery, we also use the same idea. We use non-sodium ion conducting where they stabilize beta alumina because this is not a sodium ion conductor. So they can mechanical strong, and when attached to the sodium, they can form really inert pathway. So make the whole electrolyte mechanical strong. Also, when beta alumina reduced by sodium, they have an oxygen loss where they can provide oxygen. So in that case, we can form high Coulombic efficiency, also larger CCD. So we can get the CCD 7 milliamp per centimeter square. And another idea is, can we use this for also multivalence battery? Magnesium even more difficult because any solvent reduction for polymer, they will block multivalence magnesium transport. So the lithium form SCI just say it still work, but it just cannot prevent the dendrite. But the magnesium, you need to really make sure polymer not form. But if you use chloride, they are really corrosive. But if you use DME, they will reduce. So we use a new idea. We put the M4. They have a strongly bonded with the magnesium, and then they can dissolve it like remove the DME in a solvation shell. In that case, DME will not reduce, and then they can form ceramic. We can see there are no any SEA on the surface, and then they can easily highly reversibly plating magnesium. So the efficiency can reach 99.8. CCD can reach 3. Also, M4 strongly bonded magnesium, and then they can easily diffuse into the magnesium oxide. Normally, if without the organic or water bonded with magnesium, it's hard to diffuse in the transition metal oxide. So this is the same principle, whole design, surprise solvent reduction, promote salt reduction to form the metal, any metal, zinc or lithium or magnesium. If we can form SEA, we can form ceramic, and surprise capability to form polymer. And then we use same principle. We want to talk about the aqueous. Aqueous is the same thing. We do not want solvent to reduce because water reduce, they form gas, they limited the window. So we want same principle, surprise water reduction, so we can have a large window. Because salt reduction at lower potential and water reduction high potential. So when you reduce the potential, the water reduced to form gas. Salt never have a chance to reduce. So if we increase the concentration of salt, and then we have a possibility increase the reduction potential of the ion. And also when water reduce, they form local alkaline environment, and that environment promote the TFSI reduction. So they can have a chance to form lithium fluoride. So the principle is the same as organic. And the same idea when you have the cathode side, you increase the potential, and then TFSI is hydrophobic, the ion. They absorb on the surface, and then they block the water absorb on the cathode side, and then they reduce of the capability to oxide into the oxygen. Then we form 3 volt, the window. We demonstrate use MMO, MOS, and we also try to further increase the energy density by use high capacity air cathode and zinc anode replace MS, and we can get a really stable zinc air battery because the water bounded by lithium, they will not evaporate, and then we can open to the air. Zinc, we have a zinc ion, but most of the water bounded by lithium, so zinc can easily plating, stripping without the reduction of the water. But if we use commercial available organic cathode and anode, we have to use the MMO, cheap MMO, and LTO. But LTO reduction potential 1.5, so this is still too high. Then we add cheaper urea. Urea is not flammable, and when we add it, we can reduce the concentration from 21 to the 4 molar. And also, because they can form eutalic with the water, also TFSI. So they are, even we increase the urea, reduce the concentration to 5 molar, the viscosity is still not high. We can reach to the 1.4 potential. Then in that case, we can form MMO LTO cell. So this is a commercial soft cell. We can put a high loading 2.5, and 1C, we can cycle really stable. And we also do the self discharge test, and we believe when you have a less electrolytes in the commercial lean electrolytes, they have a same self-discharge rate as organic. And we also further increase the energy density, develop a new kind of cathode, and this cathode transition metal free and capacity doubled, and potential lithium deletion potential similar as a lithium magnesium oxide. The principle is, if we put the lithium bromide, the lithium chloride mixed with graphite together, and use the water in salt electrolytes, and then they can take a little bit of water from water in salt and form like aqueous, the electrolytes cover on the surface. And then during the charge, bromide, chloride insert into the graphite, lithium go to the anode side. And we got a very stable cycle. Right now, we transfer to the organic because we want to use this in a traditional current lithium-ion battery. So we successfully transfer this cathode to the organic, and we can charge this cycle very stable. And the same principle as the last slide, we show magnesium and multivalence battery. You have to, best way is no SEI. If you really want to form SEI, only way is ceramic. And so for the zinc in the aqueous, they have the same problem. We do not want them form lithium dendrite, but you have to form SEI. SEI only zinc, the forbic SEI will block zinc dendrite. We use the exact same principle, and then we use ammonia OTF and dissolve into the just 0.5 molar, dissolve into the 1 molar zinc OTF. Then we can form zinc fluoride, and they have a high interface energy, and they can block zinc dendrite, and also can prevent water penetrating inside. The air uses the exact same principle as water in salt. While we have a high potential and TFSI or OTF, the ion is hydrophobic. They can block the water on the surface, and so they can avoid water oxidation. Water not involved, and then oxygen redox change from 4 electronics to 2 electronics. Then the reaction very fast. And after that, we think, what is the next? So the next, beyond the water in salt. Water in salt, they have another challenge is they can break the water. So water will not freeze. But at low temperature, ion, cation easily form a salt deposition. And we try to block this bond. So we develop high entropy electrolytes. That electrolytes can operate at -80 to +80. That make them keep the water in salt property and add additional benefits at a very wide temperature range. Okay, so the company licensed technology microcell silicon and transition metal free cathode, and also I've made oxide and the battery. So I think my time is over. I just go to the last one for the acknowledge the funding support, and so I just appreciate your time. So that is I end my presentation. Thank you.